Hello. So now I want to talk to you about Newton's third law and free body diagrams. So in our previous lecture we talked about Newton's first and second law. So remember that the first law is basically an object in motion will continue to stay in motion, or an object at rest will continue to stay at rest unless acted upon by an outside force. Okay? Newton's second law defines the equation which relates force and acceleration, and it says that the sum of the forces on an object will equal the mass times the acceleration. So in this lecture I want to cover the third law, and I also want to cover free body diagrams. So first, what is a free body diagram? A free body diagram is the picture that you'll draw whenever you have any of these force problems from chapters 4 and later. So what it is a picture that represents all the forces that are acting on a particular object. So you're going to model the object as sort of a point particle, and you'll draw all the forces acting on that object as originating from that point. Okay? The forces are vectors, and so they're going to be represented by arrows. And of course the length of the arrow shows the magnitude of the forces, and the direction that you draw the arrow in shows you the direction. So this is the most important step, I think, in solving problems with Newton's laws. You have to draw that free body diagram. When you draw your free body diagram, you're effectively also choosing an origin for your coordinate system, so that's very helpful. Make sure to only include the forces that are acting on the object of interest. If you draw other forces acting on other objects in the problem, you might just confuse yourself. Include any field forces that are acting on the object. Later on, in the second semester, you'll get into forces such as the force on a charged particle. But for now, the only field force that you're going to deal with is gravity. Okay? And you want to pick that coordinate system and show the directions of your axes. And then outside of the free body diagram forces, you want to show which direction the object is traveling in. And so here, the forces are represented by the blue arrows, and then the motion, the direction of motion, is represented by that gray arrow. And notice that the motion force vector doesn't originate from the same point as the rest. It kind of helps you figure out which vector goes with what. Okay, so that's free body diagrams. Now let's move on to Newton's third law. So Newton's third law is the action-reaction law. Anytime a force is exerting on an object, that force is caused by another object. So when one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. Another way of phrasing it is, for every action, there is an equal and opposite reaction. Okay? So here in this picture, it shows a hand pushing down on a desk. Okay? But if you do this, if you take your hand and you push down on a desk, you'll feel a force in your hand from the desk. Okay? And if you push hard enough, it'll hurt. Okay? That's the desk pushing back on you. Alright? So you push on the desk pushes on you. That's action-reaction. And in fact, it's the heart of something that we call the normal force. Okay? A normal force is a force exerted by a surface against an object that's pressing against it. Okay? It acts perpendicular to the surface. Perpendicular and normal are synonyms. Okay? So normal forces means perpendicular forces. This force, the origination of the force, comes from the molecular bonds in the material, and it also, when you're standing on a floor, keeps your feet from sinking through the floor. And ultimately, it comes from the repulsion of the electrons in the two surfaces pushing away from each other. Okay, so it's electromagnetic in nature. Normal means perpendicular. So normal forces are always perpendicular to the surface that causes them. That means that if your object is resting on an incline, okay, the normal force will point perpendicular to the incline, as I show here in this diagram on the left, where there's a block resting on an inclined plane. Okay? All the forces acting on the object include the weight, which is straight down towards the center of the earth, friction, which is acting up the incline, okay, since the block's trying to slide down the incline, and normal force, which is pointing perpendicular to the incline. Also, here, with the TV resting on the table, you had the force of gravity acting down and the normal force acting up. And the normal force would be the surface from this invisible table here that's pushing back up on the monitor. Okay, so Newton's third law. Make sure that you understand that a key to the correct application of the third law is that the forces are exerted on different objects. And make sure that you don't use them as if they were acting on the same object. Okay, so here in our example, there's an ice skater, and she's pushing on the wall. And because she pushes on the wall pushes back on her. Now what would happen in this case is, as long as she's not holding onto the wall, as long as she just gives it a push, right? She pushes on the wall, but that causes an action-reaction force to push on her. Since there's nothing gluing her to the wall, that action-reaction force will cause her to go backwards, all right? So in this case, it's the reaction force to her push that causes her motion. If you instead assumed that the action or reaction forces were on the same object, then there would be a force one way and a force the other, and they're equal and opposite, so she wouldn't go anywhere, right, because she would have no net acceleration. So it's important to realize that the action-reaction forces act on different objects. Like for the example of the hand on the table, my hand pushes down on the table, right, so that's a force on the table, and then the table pushes back on me, and that's a force on my hand. Newton's third law can also be used to explain a lot of interesting phenomena, such as rocket propulsion. So rocket propulsion can be explained by the hot gases that are spewing out the tail of the rocket, okay, actually causes the thrust, which is the force that propels the rocket upward. It's a reaction force, the thrust that propels the rocket. So here's a free body diagram for thrust, okay? Thrust is a force exerted by gas exhaust on rockets or jets, and that's created by igniting the fuel, okay? So for our space shuttle here, we're going to assume that the space shuttle is going straight up, okay? So here I have my coordinate system chosen, and the circle is just supposed to represent the space shuttle. Remember that you don't need an elaborate drawing, the point is good enough. So here's my little circular blue rocket. The thrust is propelling it upward, that's the red force vector, okay? And then gravity is pulling down on the object. These forces aren't the same length. Okay, if they were the same length, then that would mean the thrust equals gravity, and the rocket wouldn't launch, it wouldn't go anywhere. So the longer vector, represented by the thrust vector, indicates that you'll have a net acceleration upward. And then I've drawn this net motion arrow in gray over here to the left to indicate which direction the rocket's moving. Another kind of force is the spring force. Springs can be used to calibrate the magnitudes of forces, and we'll learn more about springs later. But basically, it's easy enough to understand that if you compress a spring, it'll push outward, okay, so it'll push back on you, and when you pull a spring, it'll pull inward. So springs like to stay at their equilibrium length, and they'll exert a force either inward or outward to try and maintain that equilibrium length. Springs are really important in physics. They serve as a model system for a lot of other systems. We use them, for example, to represent bonds. Okay, so here's the spring over at the right, and in the top image here you see the spring and it's at its equilibrium length, which I call L, okay? Now, if you pull the spring outward, that's the middle, okay, then the spring has an extended length, and the extended length is delta x. Okay. Now, in order to pull the spring outward, I had to exert a force, and that's this blue arrow indicated by an F here. So the blue arrow is my outward force in the spring. But action-reaction, okay, the spring pulls back with an equal and opposite force on me. So my force is F, and its force is F sub S, trying to pull me back, okay? And then here in this drawing in the compression, I had to push the spring in, okay, to make the spring shorter, and the spring wants to push back on me because it's trying to go back to its longer equilibrium length, and that's the force of the spring there on the right, okay, which is the red vector. All right, tension is another kind of force. So if you have a string, rope, or wire, and it's pulling on an object, like in the image here with the towboat and the big tow ropes towing the larger boat, ultimately this is also from molecular bonds. Okay, it's the strength of the cable or rope or what have you, and how tightly they're bound to one another. And of course, nowhere is this illustrated more clearly than if you pull too hard and you exceed how much tension that the rope can take and you snap it. Okay, so you've broken bonds inside the rope when that occurs. Another thing to realize about tension is that tension in a rope goes both ways, okay? So you pull the object and the object pulls back on you, action, reaction. If I've got something connected by a rope and I pull on it, then the rope pulls back on me. So the tension in the rope goes both ways at all times. Let me show you what I mean by that in this example, which is a stoplight, okay? So in this example problem, the stoplight is suspended by 3 different cables, okay? Cable 1, Cable 2, and Cable 3. So Cable 1 is here on the left, and it's at an angle of 37 degrees. Cable 2 is on the right, and it's at an angle of 53 degrees. And then Cable 3 kind of hangs straight down, supporting the stoplight. I'm going to draw a free body diagram at the knot where the cables are connected, okay? So the tension in Cable 1 is pulling up and to the left. The tension in Cable 2 is pulling up and to the right. And the tension in Cable 3 is being pulled down by the weight of the stoplight, okay? But if you look at the free body diagram for the stoplight, okay, now the stoplight here has gravity acting down on it, mg downward. And then what's pulling up is the tension from Cable 3. So you can see that depending on what I draw my free body diagram on, the tension in Cable 3 pulls down on one side and it pulls up on the other side. So the tension in the cable goes both ways, and it does that in all 3 cables, but I'm just drawing the example for Cable 3. Okay? All right. Let me do another example problem for tension. And this one I'm going to do a full example with the free body diagram and applying Newton's second law to solve. All right. So this one's called weighing a fish in an elevator, which I know is something that we've all done. All right. So a person weighs a fish, and the fish has a mass of 4.08 kilograms, and it's being weighed in an elevator. So evaluate what the scale says that the weight of the fish is. If the elevator moves with an acceleration of 2 meters per second squared up, or if the elevator is instead accelerating downward at 2 meters per second squared. So I've got 2 free body diagrams here. One for when the net acceleration is when the elevator is going up, okay? And one is the net acceleration when the elevator goes down, okay? So for the one on the left, here's my fish. Here's my free body diagram for my fish, and I've got tension up and mg down. And I've got basically the same free body diagram, tension up and mg down, for when the elevator is going down. Now the first step in all of these types of problems, when you have to do the full solution, is to take your vectors and write the vectors in terms of their components. Okay? Now this one's not too bad because these vectors, the tension and gravity, they only point in what I'll call the y direction, basically up and down. So I'm going to go with the conventional choice and choose up as positive and down as negative. So the y component of my tension, I'm just going to say as plus t, because this is our unknown. We don't know what the tension is. What the tension in the rope is will be how much the fish weighs, okay, what the apparent weight of the fish is. That's what we're solving for. Now we have the tension up, and then we have the force of gravity acting on the fish. The y component of that would be m times negative g, which in this case we do know. The mass of the fish is 4.08 kilograms, and gravity is negative 9.8 meters per second squared. Remember that it's negative because it's acting down, and this is our negative y component. All right? Now we have our vectors. Now I'm going to apply Newton's second law. Newton's second law says that the sum of the forces acting on an object is equal to the object's mass times its acceleration. I have that written out here in mathematical terms. The sum of the forces in y, in this case, acting on it, is going to equal to the mass times the acceleration. That acceleration will be in the y direction. Okay? If the elevator is moving upward, then the acceleration in the y direction is plus 2 meters per second squared. And then I multiply that times 4.08 kilograms, which is the mass of my fish. That mass times acceleration I set equal to the sum of all my forces. So if I sum my forces up, I've got tension and I've got gravity, right? So T plus T minus m times g. So that's T minus 4.08 kilograms times 9.8 meters per second squared. Another way to look at it is T plus 4.08 times negative 9.8, but I've just gone ahead and moved my minus sign out. Now I've got this full equation, and it's got only one known, and that's my tension, and so I can solve for my tension. And the tension here is equal to 4.08 times 2 plus 4.08 times 9.8. And when I solve for that, I get 48.1 newtons for the apparent weight of the fish when the elevator is traveling up. If the elevator instead is going down, the only thing that changes is that the sum of the forces is equal to 4.08 kilograms times negative 2 meters per second squared. The negative sign on the 2 comes from the fact that the elevator is accelerating downward, which is in the negative y direction. That mass times acceleration I set yet again equal to the sum of the forces, which is tension minus 4.08 times 9.8. Now I solve for tension again, okay, rearrange my equation, and I get negative 4.08 times 2 plus 4.08 times 9.8. And I get 31.8 newtons for the tension, okay, when the elevator is accelerating downwards. So the apparent weight is less when the elevator is accelerating downwards. The fish feels lighter than when the elevator is going down. This makes intuitive sense if you've ever been in an elevator and had the stomach kind of drop out, or you feel lighter in your feet. If it's a fast elevator and it starts going down, you feel lighter for a second. Or if you're going upward, you feel like your knees are going to give out on you for just a second if the elevator starts to accelerate upward abruptly and you're not ready for it. This is a really similar example to one that's in your textbook from example 4.8. This is a very similar example, except in the textbook example, the elevator has the scale on the ground. Okay? In that case, the apparent weight of the person would be measured by the normal force. All right? So you can look at that for a little further information. The next force that I want to cover is the force of friction. We'll cover this in more detail in the next lecture. But for now, let's just define the force of friction as the resistance to the motion for an object that's moving along a surface. Okay? And this is due to some interactions between the object and the surface that it's sliding across. Friction always acts tangentially to the surface. In other words, it always acts parallel to the surface. Okay? And it always opposes the direction of motion. If the object is at rest and it's a static friction, then it opposes the force that's trying to push it. Okay? Another bit that I want you to understand about Newton's third law is a little bit of notation that your book uses, and in fact that many books used. So it uses subscripts to indicate. So here there's a picture of a person and the ground. All right? So she's walking along. So what you do is the force on the person's foot by the ground is indicated by FPG, force of the person on the ground. Right? And then FGP, you flip the order of the subscripts, is the force of the ground by the person. So you flip them. And via the action-reaction on Newton's third law, then FGP will be equal to negative of FPG. And that's just because the negative sign indicates a change in direction, going in the opposite direction. So one reason that I lump this in with the force of friction is because the force that the ground exerts on the person's foot, well, that's actually the force of friction between the person's foot and the ground. Okay? If, for example, it were an icy surface, then the force that the ground could exert on the person's foot would be a lot less. And so if you push too hard and you're not wearing something spiky kind of shoe or some kind of slip-resistant shoe of some kind, then your foot will just slip on the surface. If there were no friction at all, you wouldn't be able to walk. You need the friction between your sole of your shoe and that ground, in other words, in order to push you along. Okay? So it's the friction that's pushing her forward. Finally, drag is a form of friction that exists in liquids, okay, or gases. So if you've ever stuck your hand out the window of your car and felt the air pushing on your hand as you drive along, that's drag, okay? You could also do that for any kind of medium, any kind of liquid or fluid medium, air, water, maple syrup. It'll drag, it'll pull on the object. Again, it's a resistive force. It opposes the direction of motion, and it's something that we might talk about a little bit later in full detail. But for now, just understand that drag is a resistive force that acts 180 degrees to the motion of the object moving through the medium. Okay, so that kind of sums up a lot of the forces that you'll be dealing with in this chapter and in coming chapters, and gives you an idea of how to draw these free body diagrams. In the next lecture, I'll do more of applying Newton's second law and free body diagrams to solve force problems. See you in class.